well, I'll just scratch mine out. You guys have the white space. Okay, in the space on that page, page 289, there's some rules of definite intervals. I'm going to write those in this space. These are rules that help you break apart intervals. Okay. You can see at the top of the page, above the chart, if we have f of x dx evaluate from a to b, if for some reason your bounds are backwards, b to a, that would be the same thing as integrating the negative f of x dx. So the negative's outside because any multipliers you can pop outside. Kind of like when we did derivatives, you can pop out the coefficients out in front. Okay, so the constant rule. The constant rule is if we are integrating some f of x, k f of x dx from a to b, you can pop out the constant in front of the integral. And it'll be k times the integral of f of x from a to b dx. Okay? Same with derivative. That little multiplier, if it's a constant multiplier, you can pop it out in front. If we have a sum or difference inside the integrand, the integral thing here is called the integrand, you can separate them. So if we are integrating some function f of x plus or minus some function g of x dx, if I have to have a dx, but since that's like our width, it has to be times to everything, so you need either parentheses or brackets around the functions. If I'm adding two separate functions or subtracting two separate functions within my integral, I can integrate them individually by using the same bounds, a to b, of f of x dx separately, plus or minus the integral of g of x dx evaluated from a to b. Does that make sense? You can break them up and do them separately. It makes your life a little easier that way. Another one, there is they call it additivity. Okay? Additivity. If you have two integrals being added and the upper and lower bounds start and end at the same place, so if this one goes from a to b, and it's being added to another integral that starts on the first one's ending point. First one's upper bound was b, so this one would have to start at b, and we integrate from b to c of, say, it has to be the same function as well, f of x dx. As long as these functions are identical, and the second one starts where the first one ended. You guys see that? Exactly. You would be able to integrate from a to c because it's the exact same function. You can just squish it down into one integral. And I think that's the last one I wanted. Yep. Okay? Those are some nice little tricks we can use. Okay, we filled this in last time on our notes. 3 ways we've learned to integrate. What's the first way we learned to integrate? Riemann sums, the rectangular approximation method. the estimation. It's not exact. Estimation. We have Riemann sums. What's the second way we learn to integrate? Geometry, using our knowledge of areas. And today we're going to be working with the antiderivative. All right, so quick review. That we have three functions, right, or not functions, expressions. Find the antiderivative of each, which is different than the derivative. Anti is going reverse. So we actually did this one earlier. Jonathan, you already told us this. What's the antiderivative of x squared? 1/3 x cubed. Now, if we don't have any bounds, we have a constant plus c. Okay. What about the middle one? What? We know it's going to be x to the fourth. Is it just x to the fourth, or is there going to be a constant? Okay, yeah, that's actually a different constant I was thinking about. I should have said coefficient. That's the C word. Is there going to be a coefficient? No, because if you bring the 4 in front, it's there, 4x cubed. Okay? What about x to the 1/3 power? Okay, so the exponent has to increase, so 4/3. When we take the derivative, it decreases by 1. When we do the antiderivative, it increases by 1. Plus c. So if I bring down the 4/3, though, I don't get that. So we're going to need a coefficient. What? So if I bring down the 4/3 and multiply by 3/4, the 4's cancel out and the 3's cancel out. Okay, so does anyone notice a pattern that's happening each time we integrate a polynomial? Like, specifically, we already know, we figured out the degree, I think. But what's the pattern happening with the coefficients? Especially the first one and the last one. Can you see a pattern? Okay. What does this have to do with the exponent? It's reciprocal of it. What does this have to do with the exponent? Reciprocal of it.
When the antiderivative, or when the derivative has no coefficient, then
What actually happens is we have a power rule. If we're integrating some x to the n dx, notice I have no bounds there. We don't have a lower bound and upper bound. Then if it's not a definite integral, then we have this plus c. I get x to the n plus 1. We know the power will increase. And then whatever that new power is, you divide by the new power. Or you could say, the way you guys are saying, reciprocal. So it'd be 1 over n plus 1 times x to the n plus 1. So you think whatever your integrated new power is, you have to remember to divide by that. Okay? Now, today we're going to talk about the fundamental theorem of calculus. There are two parts. Today we're doing part 2. Next time we'll talk about part 1. Using the antiderivative method is referred to as the fundamental theorem of calculus. Fundamental theorem of calculus is the reverse of just the derivative. So that's what we call it, the antiderivative. Fundamental theorem of calculus. If, here are the stipulations, if f is continuous, at every point on the closed interval a to b, if f is continuous at every point on the closed interval a to b, and Now, I talked about last time the difference between little f and big F. This one has to be little f. When we integrate, we get big F. Okay? And if big F is any antiderivative of little f on that same closed interval a to b, if f is continuous at every point on the closed interval a to b, and if big F is any antiderivative of little f on the closed interval a to b, then here's how we do integrals. Integrating little f of x dx from a to b. Has anyone read up on this? What? Okay, you get big F, but it's evaluated first. Big F is first evaluated at B. Actually, I'm going to write the intermediate step here. We get big F of x evaluated, that tall line means evaluated, from A to B. So essentially you take big F and you plug in B, and then you subtract big F evaluated at A. Okay? They also call this the integral evaluation theorem, but I've never heard of that until I read it in the book. So we call it integration or antiderivative. This is a fundamental theorem of calculus. When you integrate, you get the capital F. And your bounds, you insert in the upper bound first and subtract the evaluation with the lower bound. That's the order. Okay? So we're going to try some on the next page, I believe. Yeah. Flip it over. The first one we're going to do in two ways. The way we already know, geometry, and then we'll use the new way to show that it comes out the same. 2x plus 1, we're going to evaluate that from 0 to 3. Okay, Alex, how would we graph 2x plus 1 so we can integrate using geometry? So we have 0, 1, that y-intercept, and then what do we use after the y-intercept? Yep, so we're using the slope up to right 1, then, so that's 3, up to right 1, 5, up to right 1, 7. And it's linear, right? And it wants us to evaluate from 0 to 3. So that area. What shape is that area? Trapezoid. Remember the area formula for a trapezoid? 1/2. It's like a triangle, but we have two different bases times the height. Now, make sure the bases have to always be parallel to each other. So, Ariel, what are the lengths of the two bases? 7, yep. Because right here is length 1, right here, and those are parallel to each other. We can show parallel with little arrows, is length 7. 1 plus 7 times the height has to be perpendicular. Is the line from the graph 2x plus 1, is that perpendicular to the parallel lines? No, you have to use the base. It has to, base and heights has to be perpendicular, and that is length 3. Okay, so what does, when we integrate using geometry, what do we get? What? 12. Yeah. Okay. Now we're going to use our new friend, the integral, using fundamental theorem of calculus on the same thing, and see how it's done, and we should make sure we get 12. Okay, this is a polynomial. So when we integrate, using that power rule we just discussed, we take 2x, increase the exponent, so it becomes what? X squared. Now that new power squared, we divide it by that new power. Plus 1, we increase the exponent. Well, this has how many x's? Right now it has 0 x's, so we increase it to 1, which has a power of 1. Divide by 1 is still just x. But all of this, you need to parenthesis or bracket that. All of that needs to be evaluated from 0 to 3 from the given closed interval. So if I simplify, I have x squared plus x evaluated from 0 to 3. Okay, so since there are multiple terms, you have to put it in grouping. The first group is 3 squared plus 3. You start on the upper bound. Does that make sense? Then you subtract. This is why we need the grouping, because there's a subtraction. We have to make sure everything's subtracted. 0 squared plus 0. So first we do the upper bound, subtract the lower bound. Any questions? And because we have a nice number 0, that cancels out. 3 squared plus 3 gives us 9 plus 3, which is what? 12. Now, if you do this by hand and you show all your work, you don't have to write the antiderivative equals this. It would be nice if you did. But on the AP test, watch out for it. If you use a calculator, you will not get credit unless you actually write this. On the AP test, if you use a calculator, on the calculator section, you will not get credit for the 12 unless you actually use the setup of the integral. You have to handwrite that. Okay? And we got 12 on both, right? Okay, let's look at number 2, a trig function. Actually, 2 and 3 are trig functions. Okay, number 2, the integral of sine. Think what, if I took the derivative of some trig function, what would give me just positive sine? Negative cosine. You can't do positive cosine because when you take the derivative of cosine, it changes to negative sine. So you have to make sure f then becomes negative cosine. We still need the x. Do not drop that x. From 0 to pi. Okay. Now we plug in first negative cosine. Which value do I plug in first? Pi. I plug in the upper bound. Subtract. Parenthesis again. So each, the upper bound put in parentheses, the lower bound put in parentheses. Negative cosine 0 equals. I should put an equal sign. Okay? For me, I always need to draw a little graph. What does the negative cosine graph look like? Does it start at a maximum or a minimum? Regular cosine does. But negative cosine goes like this. Okay? Here is pi. So negative cosine of pi is how high? 1. Minus negative cosine of 0 is how high? Negative 1. So we get 2. Interesting. Do you remember the notes from last time I told you to memorize something? The integral of sine evaluated from 0 to pi is always 2. That was one you're supposed to integrate, memorize. And now you can see why. It is 2. Okay? But this one is 0 to 2 pi. So the integral of sine, we've already done, is negative cosine x. This time evaluated from 0 to 2 pi, integrated from 0 to 2 pi. Okay, Claudia, what do I plug in first? Good. Make sure that's grouped. Subtract the grouping of negative cosine 0. We've already found negative cosine 0 is negative 1 minus a negative 1. But what about 2 pi? That is negative 1. So we have a subtract a negative, wiggle, squiggle, and we get 0. So for good practice, so we don't mess ourselves up when we're doing calculator, if we just do it every single time and rewrite this every single time, then we should have no worries getting the points on the calculator part. Okay, flip it over. Sweet, we're almost there. There are M&Ms coming up, don't you worry. They are coming. Alrighty. If we were taking a derivative of 1 over x minus 1 over x squared, what would you do first? If we want, move them to the top. Same thing with integration, moving them to the top is easier. Okay, so this becomes the integral from 1 to 3 of, in parentheses, x to the negative 1 minus x to the negative 2 dx. These parentheses are important because it's length times width. The width is dx. The length is x to the negative 1 minus x to the negative 2. That has to all be in parentheses because all of it is times by the width, dx. You need those parentheses. Okay, let's apply integration using that power rule we talked about. X to the negative 1, we increase the power, 0, and then we divide by that 0, minus x to the negative 2, we increase the power, so it'll be negative 1 divided by that power, negative 1. And integrated, and if I do brackets, I can put those numbers just straight on the bracket. Okay, now what's the problem with this? Divide by 0. This here is undefined. How in the world can we subtract something from something that's undefined? Well, we actually know that 1 over x is the derivative of a special function. Natural log x. Okay, so that's something you should know. When you integrate 1 over x dx equals natural log x plus c in this case, since I didn't put any bounds on it. So now it's not going to work. Instead, we get 1 over x minus and the x over negative 1, which is just the same thing as plus, and x over negative x to the negative 1 power, is that just, oops, I didn't write natural log, sorry. Natural log x plus 1 over x. The reason it's 1 over x is because this is x to the negative first power, so that brings down. Evaluated from 1 to 3 equals. The reason why, no, never mind. Okay. Read. If we use our integrations bounds from 1 to 3, well, what do we write next? Upper bound first. Okay. Evaluating at 1. Okay, is this good? Parentheses. That first grouping, maybe not as important, but the second grouping, very important. Equals natural log 3 plus 1/3 minus natural log 1 minus 1, because we need to distribute in that negative. We have some like terms. 1/3 minus 1, or maybe you can think about it as negative 1 plus 1/3. Joanna, what's negative 1 plus 1/3? Okay, so we start at negative 1. You're warm. Negative 2/3, yep. Now, is natural log 3 and natural log 1, are they like terms?
Yes.
No, their parts don't match. Their parts don't match. Their one is log base e of 3 plus log base e of 1. Their parts don't match. Well, if they were both 3 and they had like numbers out here 4 and 2, then we could add them 6 log base e of 3. So their part has to match. So no, they're not like terms. Plus natural log 3 minus natural log 1. And unless the directions say something about, and I'm going to put be a good example here. Put 1 to 3, 1 over x minus 1 over x squared dx. Unless the directions say round to decimal, and if this is non-calculator portion, there's no way you know what natural log 3 minus natural log 1 is, so I would leave it exactly like that. Okay, will you guys go and try, please, number 5. Number 5, just a heads up, you have to know your unit circle. Okay, try number 5. Work with a partner. Try number 5. What's the integral of cosine x dx? And then integrate it from 0 to 5 pi thirds like it asked for. Okay, I'm going to go grab your review. Okay, does anyone think they have it? Come up to the board and draw it out. Where is it? It's over there. Anyone? Anyone? Oh dear. Okay, did you at least get if we integrate cosine x, what do we get? Sine x, because when you take the derivative of sine, it stays the same sign. Positive. Yeah, haha. And you need to be doing this bar, integrate from 5 pi thirds, or 0 to 5 pi thirds. So sine of which one first? The upper bound, 5 pi thirds minus sine of 0. Again, know your graphs. Sine 0 is 0, so minusing 0. Now 5 pi thirds, that's where you got to know your unit circle. Maybe, I can't remember. So 5 pi thirds is almost 2 pi, right? So it's in this quadrant. 1, 2, 3. Since we're on the bottom, we start 1, well, I'm going to give them all their little over 2's. 1, root 2, root 3, 1, root 2, root 3. Which ones are positive? The x's are positive. The y's are negative. So this is my point. Now, question is, where is 5 pi thirds? Which line is it? Top one, middle one, or bottom one? That's 2 pi minus 1/6. It's this one. And alphabetical order, cosine theta, sine theta. So sine is actually root 3 over 2. Negative, yes, thanks for catching that. Negative root 3 over 2. Okay, so our integral from 0 to 5 pi thirds, please write this every time so that you're always used to it, so you won't lose points if it's a calculator portion. That. Okay, 2 more and then we'll just write a definition and then do our activity. We should be good. Any questions on that one? It's like we need to do some unit circle practice. Okay, number 6. We're integrating e to the x plus x to the 2/3. Remember when we're integrating, we're really finding the area under the curve. Always keep that in mind, okay? So if you graph e to the x, it's an exponential plus 2x to the 2/3. Those morph together. We're integrating underneath the curve from 1 to 3, the area. All right, so let's do e to the x. If we integrate e to the x, what do we get? Because the derivative of e to the x is e to the x. So that's another thing. Maybe we should put that on the top here. We have this one. Add another one. Integrating e to the x dx is e to the x plus e. E to the x is a nice one because it's just itself. Okay, so we get e to the x. Now with our x to the 2/3, we have to increase the exponent by 1. 2/3, in my head, I would add 3 over 3, because 3 over 3 is a fancy 1. So we get 5/3. Now we have to divide by 5/3, which is the same thing as timesing by the reciprocal. Now make sure you bracket or parenthesis that. It's evaluated from 1 to 3. Okay, Rebecca, what do I do now? Good. Okay, minus, so I would put all of that first group in parentheses or brackets. I use brackets because there's already parentheses in there so I don't get confused. And then e to the 1 plus 3/5 times 1 to the 5/3. Yes. Now, if this is a non-calculator one, you have to know a little bit about exponents and manipulation. E cubed plus 3/5. I'm trying to get like terms here. Okay? What does 3 to the 5/3 mean? So what's the index then? You said cube root of 3 to the 5th power. What's the index? What's the index of that? Index is the number outside the grouping. No, it's 3. This is the index. The denominator is your index, which means you're grouping. So if it's a square root, the index is a 2, so you're looking for pairs. If it's cube root, the index is a 3, so you're looking for groups of 3. Yeah, so this one, there's two ways that you can do it. You can break it down on the side, and this has actually 1, 2, 3, 4, 5. And because the index, which is the same thing as the denominator, was 3, we have one group of 3 that pulls out. So we get 3 times 3 times 3 is 9 to the, I'm going to put it back in the original form, 1/3. So this becomes 3 times 9 to the 1/3. Not 9. Why did I do 9? I want to keep it as a 3. So there are 2 of them. Let's keep it as, I want to keep it as a 3. So 2/3. Because 3 squared is 9. So it's still showing that there are 2 3s. That's what I want. Because the other one, I want to get the same. To the 2/3. Minus e to the first. Minus, now this one's nice, because 1 to any exponent other than 0. Well, 1 to the 0 power is also just 1, right? 3/5 times 1, which is just 3/5. Turns out we have some like terms. What's like terms? Are the e's like terms? Yeah, the fractions are like terms. Okay, if I simplify the fraction that looks kind of hideous, I actually have 9, because 3 times 3 is 9, times 9/5 times 3 to the 2/3. And because these two have a common denominator, we can add them. We can add them. So that's about all you can do. Okay, and that's about as far as you can go without a calculator. If that's for a decimal and it's on a calculator section, then you can plug it in. So that is 1, 2, 3 of e to the x plus x to the 2/3 dx equals that. Okay, let's flip to the activity. I think, we have one more page just to write a average value of a function formula, and then we'll do the activity that has to do with the average value of a function. Is that the page you have next? This page? Okay, average value of a function is when you integrate, actually let's put here, f_av, your book puts something I've never seen before and it's silly. They put, what did they put? It was like av of v, if your function's v, or if your function's f, it'd be av of f. That's weird. I've never seen that before. We usually just do a subnote. This is the function, we're taking the average of it. Integrating f of x dx. Now if you're finding the average,
divide by the number, so
divided by the integral width. So the integral width, so say we go from 2 to 7, what's the integral width? 5. And you do that by doing 7 minus 2. So b minus a. Okay?
you put the e and a on our end as well.
Yes. That would be wise. And as we talked about, constants can pop out. Well, this is a constant. So it can pop out in front, like the one on the right. Okay, I don't think we're going to do that example down below because I like the activity better. So, flip over to your activity. Let's see, I have little cups here. Okay, this one's not on my smartboard, so what is the, Jake, would you read the top of the activity for us? Yeah, does that have instructions or something? Yeah. On the graph, the curve is f of x equals x squared plus 1. And the graph is the next page. Flip it over. There's a graph. Okay? Maybe I should have done it on the same piece of paper. This might cause an issue. So maybe you'll want to be in partners, and one person have it on this, one person have it on the graph. Using your M&Ms, you're going to fill the area between the curve and the x-axis. Compensate as best you can for M&Ms which stick above and ones that don't quite reach the curve. Because you're trying to find as close as possible the exact M&M area. Okay, so you might want to partner up so that you can both see the worksheet and see the graph. And you guys can all, I bought 2 bags, so you can all send one person to come and get 2 cups so that everyone gets their own cup. And these are my favorites, so I got these ones, so they were the same price. And you probably actually need 2 cups anyway, now that I think about it. And then you can share them. You guys can eat a cup after we're done. Yeah, I can't open it. Okay. So, with you and your partner, you're going to be filling the area underneath the curve of that graph with these M&Ms. You probably have to be in your one group of 3. Did you guys already work out the group of 3? Who needs a cup? M&Ms. You need, well, if you all want to eat your own cup. So, let's see if 2 cups gives you enough. Fill in the area underneath the curve with your M&Ms. Compensating, because sometimes the M&Ms are going to stick too far up, right? And sometimes they're going to be too far down. There'll be a little wiggle room. So compensating for underneath the curve. Oh, yes, okay. You just start at the top. Good.
For different sizes.
Oh, that's true, huh? Some of the M&Ms are different sizes, so it won't be quite accurate, but it's fun. Still, either way, and they taste good. My Christmas tree is still up as well. I don't think I can take it down till next week. I have 0 time. Okay, after you filled it in, step 2 says, now take all of those exact M&Ms, no more, no less, that you've selected for your area under the curve, and rearrange them so it's a rectangle from 0 to 3 on the graph. Take all of those M&Ms. Right now it's kind of a curvy triangle, right? A concave in triangle. And take those exact number of M&Ms and rearrange it so it's a perfect rectangle from 0 to 3.
On the Y.
On the x-axis. And you can see 3 is kind of cut off, but it's the furthest right.
Isn't that 30?
No, these are 0, 0.0, 0.5.
Okay.
Okay, up to 3. 3 is the furthest right endpoint. It kind of got cut off into a perfect rectangle. Then you're using the definition of average. Calculate the average value. You've integrated you found the area under the curve from 0 to 3. Now you're rearranging it into this rectangle. It's also 0 to 3. What do you think the average value of the function is? When we do this rectangle, how is that showing us what the average value is? Ideas. Brainstorm. How is this rectangle showing us what the average value is?
Average value of the curve?
The average value of the function. So we did this rectangle thingy. How is that showing us the average value of the function?
Does the height be the average?
Height
of the rectangle?
What do you guys think? Did the width change? No, the width was still the same whether we had it underneath the curve or in the rectangle. The width is exactly the same. What changes is the height. Okay?
It's like what's it called? Physics.
Oh, what's in physics?
So like velocity graph, you take the area underneath the area, like how far they travel. And so
Yep. There we go. So, we have our graph from 0 to 3, right? Area under the curve. So if you take those, it's not cooperating. Okay. If you take your M&Ms, the rectangle is shorter, right? And something like this. The width didn't change. What changed was the height. The average height times the width is the same as the area under the curve. Did you add M&Ms or subtract M&Ms? So the width times this average height is the exact same as the area under the curve. So the width times the average height is the exact same as the area under the curve. So what was the area under the curve that you guys got? How many M&Ms do you have? 43? Is everyone about 43?
43.
Okay. So find the area under the curve with our M&Ms from 0 to 3. X squared plus 1 dx. We got 43 M&Ms.
43 M&Ms? Oh, we want that.
Now let's calculate the average value from 0 to 3 of x squared plus 1 dx. The average value we have to divide or multiply by 1 over 3 minus 0. Okay, 3 minus 0 gives us 1/3 times the integral. What's the, if we integrate x squared plus 1, we increase the power and divide by 3, which is just like 1/3, plus increase the power, divide by 1 doesn't do anything, evaluated from 3 to 0. The 1/3 out front, any constant multipliers that we pop out front, just come along for the ride. You don't have to use them until the very end. So when we evaluate at 3, 1/3 times 3 cubed plus 3, subtract 1/3 times 0 cubed plus 0. That 1/3 just comes along for the ride for a while. Are you writing this on your notes? So we get, you can take them off, we're done with the M&Ms. You can eat them. We get 1/3 times, let's see, 3 cubed, isn't that 27? Plus, how could I write this 3 to have a common denominator? Can this 3 have a common denominator of 3? What divided by 3 is 3? Isn't it 9? You guys are too busy with your M&Ms.
Yeah.
27 plus 9 is 36 divided by 3. I get 36 over 9, which is just what? 4. So on M&Ms, it was 43. But really, it is 4.
No, that was
Oh, that's right. Yeah, sorry. You're right. This was the integral, and this was the average. So what you should have seen was the height was 4. You're right. Okay. This one doesn't have that on it. Is the average value you calculate approximately equal to the height? Yes. Right? Give a geometric representation. That's what I already drew. Okay. Okay, when you're done with that, flip to the one that's number 9. The very last page is some information on the difference, just to read, to clarify the difference of average value of a function versus average rate of change, because they're different. What is another word for average rate of change? Like your slope, okay, tangent line. It's different than average value of a function. So the last page is just a paper you should read through to clarify the difference between average value of a function and average rate of change. Let's look at number 9. It'll be the last one we do. It has to do with average value. Find the average value of this function. Is everyone done writing these? No? Man, you guys are brave putting them on the desk. You know how many germs are on the desk?
I'll eat them all if I don't.
Okay, look at number 9. Find the average value of a function on the interval 0 to 3. Again, we know average value of the function is 1 over b minus a of the function evaluated from a to b. Just jumping to 9. We're skipping number 8 because we don't have enough time. And I like 9 better than number 8. Okay, so we just need to integrate f ab what are our bounds? Ethan, what are the bounds for integration? But for this problem, it would be 0 to 3. So for our fraction, we would put 1 over, for averaging them, 3 minus 0. Okay. We're always dividing by the width of the interval, which is 3. From 0 to 3 is a width of 3. F of x is, in parentheses, x minus 1 squared dx. How are we going to integrate x minus 1 squared?
Break it out.
Yeah, distribute it out. Make it a polynomial instead of this extra, like, it looks like reverse chain rule maybe. That's too difficult. It's way easier to multiply it through. So we get x minus 1 times x minus 1 dx. Running out of room, so draw a nice little arrow so we can follow the work, right? You guys are getting better at helping me follow your work. 1 over 3 from 0 to 3. Okay, I need someone to multiply those out. Amisha, what will we get when we times x minus 1 times x minus 1? We can sing the song, it's true. Okay, Kyle's already sang it for us. Amisha, you're up the hook. Kyle, sing the song for us.
We're just square the first one, square the last one, 2. In between the first and last is first times last times 2.
Good. Square the first one, square the last one 2, in between the first and last is first times last times 2. Now this is just a polynomial. Polynomials are easy to both take the derivative of and to integrate. Those are your friends. When it's not a polynomial, it gets a little more difficult. This 1/3 again just comes along for the ride. It's just a multiplier. You don't multiply it in until the end. Okay, but don't forget that it's there. All right, John. If we integrate x squared, what do we get? Oh, he's done this one twice already. I'm going to give you a different one. Jake, you're Jake. Jake, integrate x squared. Yep, increase the exponent and divide by that new exponent. Now to John. Negative 2x. Integrate that one for me. Negative x squared. Because if we do 2 divided by the new exponent 2, it's just 1, right? And this is subtracting, so it'll be negative x squared. Plus, Joanna, integrate the 1. It's x to the 0. Keep that in mind. You up the power. X to the first. 1x to the first. Divide by 1, which is just x to the first. Evaluated from 0 to 3. If you use brackets, you can put the numbers right on the bracket. If you use parentheses, you have to do a vertical line. No, you don't. Yeah, you don't have to put that exponent. Okay, which one do I plug in first, 0 or 3? Good, you should always be using that top bound. 3 cubed minus, and I'm going to need to bracket this, 3 squared plus 3, that group. Then we subtract what?
1. 0.
0. But the group would be 1/3. Yeah, it will end up equaling 0. One-third. This seems like a problem we've already done. Didn't we just do this one? Was this the one we did on for M&Ms? No? Different? Okay. 3 cubed is 27 over 3. I sorted the last example out of 27 over 3. Minus 9 plus 3. Isn't 27 over 3 just a nice pretty number? Isn't it 9? And so these cancel, because 9 minus 9 is 0. So we have 3 over 3, which equals 1. So I would put equals 1. F av of all that good stuff equals 1. At the very bottom it says, when does a function obtain the average value? It obtains this average value of 1 when the function equals the x value. What was the function? X minus 1 squared. When that equals the average value, then we will obtain, that's when we obtain the average value, when it equals 1. So if you solve square root, x minus 1 equals, what's the square root of 1? No. What's the square root of 1? Plus or minus 1. Then if we add 1, be very careful. When you add 1, where does it go? Does it go after the plus or minus 1, or does it go before the plus or minus 1? It goes before. 1 plus 1 and 1 minus 1, so we get 2 and we get 0. The average value obtains this in 2 places. We do have a final, the last class of the term next week. So here is a review on the final. There will be a little bit of integration. Take your M&Ms with you.
Thank you.
Okay, next time on Tuesday I will have solution keys for you on this, but you should be trying it yourself first. Oh crap. Yep.
What are we turning in?
If you need to run the class, but if you have a sec, turn in 6-1. Yeah. Anyone want more M&Ms? Today's my sugar day, so I'm like, I'm gonna eat sugar. Okay, thank you. Extra. Okay, thank you. Do you like the M&M activity? Is that a keeper? Okay. I thought the other way was boring.
What was the other way?
Just working problem after problem after problem, like we usually do. I found that last night. I was like, ooh, I like this. Because then it gives you a visual, a hands-on, like you can actually understand what's going on.
Are bigger, so it's like less. Not those little tiny M&Ms.
Wow, go for it. I bought 2 bags, so it looks like I'll be giving rewards for M&Ms.
What is your schedule for like after school? Because I know I didn't make it the last week. I come home back to my work.
Oh, well, you can come correct any day after school next week. I'm usually here anyway. Correcting work's not a big deal. Oh, Monday, because I had a hair appointment. Yeah, but that only happens every 4 months. Yeah, today I am leaving early because it's my opening night and I only got 3 hours of sleep last night, so I need to sleep.